All right, 1.4, we've learned how to evaluate limits a little bit algebraically. We've also learned how to evaluate them from a graph and, of course, from a calculator, which we don't always have. We can sneak up on it. But 1.4 is all about algebraically evaluating limits. Now, the first thing that we are going to always attempt is direct substitution. And the reason that is because if a function is continuous at a point, what do we know about the limit value and the function value? They are the same. Yeah, so unless it's like a piecewise function where the exceptions are always made, if you plug in and you get an output 99 times out of 99.5, it's going to be the function value. So what types of things will prevent us from getting an output? Well, a 0 in the denominator, of course, is going to be a problem. 0 over 0 and infinity over infinity are the two indeterminate forms. And we'll go ahead and write that there, indeterminate, A-T-E, indeterminate forms, that we're going to be interested in trying to reconcile. Those are the only two that we try to reconcile for now. There will be other indeterminate forms coming along. But let's see why those are the only two. If I get a 0 in the denominator, but a non-zero in the top, the function value won't exist, but what can be said about the limit? What's non-zero over 0? Non-zero over 0 would be a vertical asymptote, and the conclusion is determined. It's either infinity or negative infinity or D and E. So we know that. If we get 0 over 7, if we just get a 0 in the top, what's 0 divided by 7? Or 0 divided by 8? 0. So that's a conclusive answer. Infinity over infinity then and 0 over 0 are the only two right now that are going to be things that we need to kind of roll up our sleeves and try and somehow creatively circumvent to try and evaluate the limit, because it means the limit may exist. And in the case of the whole, of course, we know it actually does, and we're trying to find the y value of the whole. So 0 over 0 does not mean D and E in terms of the limit. It does for the function value. Okay, so never not first. The first thing we do is what? Direct substitution. All right, now we're missing some negatives throughout here, and I've spotted a couple already, so I don't know why that is, but we'll deal with them when we get there. All right, so here we go. The limit as x goes to 5 pi thirds of cosecant of x. Well, you plug it in and you get cosecant of 5 pi thirds. And is that a numeric answer? Yes. Yeah, it is. And of course, it's equal to what? Negative 2 root 3 over 3. Fantastic. That's awesome. Okay. So the top one would be a free response answer. The bottom one would be, of course, the multiple choice answer. But cosecant is continuous there. So direct substitution works. This one is supposed to be negative and negative. The limit as x goes to negative 4 of the square root of negative x. Oh, it also approaches from the left. Okay, thank you. Thank you. Good. So negative 4 from a lot of negatives missing. That's crazy. I need to check that program. All right, so negative 4 from the left. Let's try direct substitution. Remember, direct substitution, if it's continuous, the left and the right and the general all equal each other. So that's not really that critical. Plug in a negative 4 for x, and you get the opposite of negative 4, which is 4, and you take the indicated root, which is positive, so you get 2. So there's your answer. Now, what does the graph of the square root of negative x actually look like, just to kind of review? Square root of x is this guy, right? Coming out of the origin? Haha, it's that way. It's going to reflect it across the y-axis, because your x's are switching, right? Think of it, if you have a negative in front of the x, your x's are going positive to negative, so they're flipping across the y-axis. So it looks like this. And what we just said is we were approaching negative 4. Oops, negative 4 from the left. So yeah, anything to the left of 0, you're going to be able to use direct substitution. So that's easy, right? Now, when is direct substitution going to give us problems? When we get 0 over 0, which means a whole, or infinity over infinity. Because these are actually what's of each other? Reciprocals. Good. All right. So example 2, and this is not necessarily a flow chart, other than example 1 is never not first, always direct sub. If you use direct substitution and you get non-zero over 0, then you know a vertical asymptote exists. So let's try that out. What would be the limit as x goes to 1 from the right? Well, never not first. Let's plug in. 1 cubed plus 1 is 2 over 1 minus 1 is 0. On a free response, then, what would be a safe answer? DNE. But because it's a one-sided limit and we know there's a vertical asymptote, we know it's going to be some type of infinity. Oh. Just to the right of 1, right? Like 1.0, 1.1 works. Yeah, that works. So 1.1 cubed is positive, plus 1 is positive. And 1.1 minus 1 is also positive. So it's going to be positive infinity. What would it be from the left of 1? It would be negative. Right. So this one has the opposite behavior on either side. Good. How about this one? The limit as x goes to pi from the right-hand side of x over sine of pi. Direct substitution gives us pi over sine of pi. What's sine of pi? 0. So non-zero 0 means there's a vertical asymptote. So even if it's a one-sided limit, a free response, DNE is a safe answer. But a multiple choice answer, again, is going to be some type of infinity. So plug in a number just bigger than pi. 3.14159. How about 3.14160? When you're doing the pi stuff, it's easier to look at the unit circle. If you're going to be approaching from just to the right of pi, you're going to be just over here in quadrant what? Quadrant 3. Okay? And, of course, pi, something bigger than pi, x is still going to be positive, right? Okay? But what is the sign of an angle that's in quadrant 3 going to be? Negative. So you're going to have a positive x that's bigger than 3.14159, and you're going to have a negative sign value. So that's going to be negative infinity, right? Negative infinity. Be careful when you're on the unit circle not to think that x is also negative, because this x on the unit circle is different than the x we're approaching. Okay? X is approaching the angle pi, which rotates over here. But x itself is bigger than 3.14. Okay, so that's kind of cool. Knowing a vertical asymptote exists. So we got direct substitution. If we get an output, that's the answer. If we get non-zero over 0, we know there's a vertical asymptote. We can handle it, even if it's a one-sided thing. So what else do we know? Well, limits at infinity. This is kind of a general summary of all the limits. These are easy to spot. How do you know limits at infinity? How can you spot them? They have x going to infinity or negative infinity. And like we just finished, you can kind of analyze the ratios. And I think there's some negatives missing here, so let's throw one in there. There's one in front of the 4 as well. Ah, okay. Thank you. That is a big negative. Okay, so when you have a ratio, you analyze the leading terms. And now we also have these other functions that we can compare relative growth rates to. But this is a power function or a polynomial. 5x squared over negative 4x squared, what's the answer? Yeah, if we assume that the negative is supposed to be there in the bottom, it's negative 5/4. And remember, without the square root, it doesn't matter if we're going to negative infinity, right? Because if we went out to negative infinity, it would be the exact same thing. Okay, and how about this one here? This is negative infinity, I'm guessing. The limit as x goes to negative infinity of the natural log of the absolute value of x. Yeah, very good. You can't plug in per se, right? But if you plugged in a negative infinity, the absolute value of negative infinity is positive infinity. And what's the natural log of infinity? This is actually composition. Yeah, it would really be the limit as x goes to positive infinity on the natural log of x, which does get infinitely large. But remember, not very quickly, right? Marginally faster than a constant, which doesn't grow at all. So that is infinity. So direct substitution kind of works there. Do you remember what the graph of the natural log of absolute value of x looks like? The natural log of x, of course, has a vertical asymptote and looks like this. But what is putting the absolute values around the x do? It's a transformation. Across the x-axis? I think you're thinking of that one. That's the one that takes all y values and takes the absolute value at the end, so that flips it up, and it would look like this. It would come down and go like that. But this is around the x. So remember, the natural log of x can entertain negative values, but if you put negatives or absolute values around here, you can now look at negative values. So this is the one that is going to graph all x's as if they were positive, yes, including negative x's. So by definition, this one has what type of symmetry? When your positive x and negative x have the exact same value. Y-axis symmetry. This is going to be an even function. So all you have to do to generate the graph of the natural log of the absolute value of x is, remember, leave positive x's alone in quadrants 1 and 4, and whatever might have been here, in this case nothing, get rid of it, reflect it across. So if you knew what the graph looks like, now you could say, heading out to the left, sure thing, you're going up to infinity. Not very fast, but you'll never get there. All right. Piecewise functions. These two, it says, are also easy to spot. Yeah, they are. They've got the the brace here, and in this case, they also have missing negative signs. This is really, really bad. Missing negative signs all over the place. X squared minus 3. Now, these are also most interesting at the x value where we're exchanging, but just because you have a piecewise function that exchanges at 2, the question could ask you at any x value, so just keep that in mind. But if it is the function limit at 2, then in this case you have to evaluate them separately, because from the left and right of 2, it's 2 separate functions. So if they ask you for the general limit here, you can do it in your head if this is all that's required. Let's see. What would be the limit from the left of 2? Direct sub? 1. And the limit from the right of 2? 2, right? So 1 from the left and 2 from the right. So does 1 equal 2? No. So what can we say about the general limit? Does not exist. And what type of discontinuity would there be? A jump, right? A jump. All right, here's another one. Oh, man. Let's see, Eugene, do you have the values here?
Yeah, it's -1, I guess. This is negative. It's just a box there.
Wow. Okay, let's try that. That's good. I'm okay with that. This is horrible. Yeah, that'll work. So anyway, if f of x is equal to this, sine of x to the left and right of -1, and 1 when it is -1, what's the limit as x goes to -1? Yes? This one's interesting because notice the limit doesn't care about the function value. The function value is -1, 1. Cool. Glad to know that. The limit is what are the roads going to? And notice to the left of -1 and to the right of -1, it's going to be the graph of sine of x, right? So it's like having the graph of Sahala, which is like this. And here's pi halves, which is like 1 point something. Yeah, I wrote pi thirds. Yeah, I meant pi halves. That's like 1.5 something. So -1 is going to be right around here. Okay, but notice what the function says. It says, okay, let's not include that ordered pair, whatever it is. Let's put an open circle and define it to be +1 there. But the limit would still be what? The old function value of sine of x there, right? Which by direct substitution is sine of -1. It's not a nice unit circle ratio, -1 radians, but it is sine of -1. So notice in this case, you can use direct substitution into the piece that defines it to the left and right, as opposed to having to look to see what it is from the left and right with 2 separate equations. Yeah. Were they messed up? I remember we had some problems early on, and I thought I went through and fixed them with a different PDF program. Okay, well, pi works. Yeah, if you work it with pi, it's going to be 0. In other words, whatever this value is here, the limit is just going to be sine of that value. Because all you're doing, you're making a hole. You're coming in with the graph of continuous sine, and you're saying when x is -1, swipe it away. But the limit is still the old y value, whatever it was. Okay, so far we haven't really done anything new per se. We're just kind of reviewing. Here's another way to find limits, right? Squeeze theorem. This is getting embarrassing right here. And then x, the x minus 1, yeah. So this is another way to algebraically determine a limit. Spotting it is like spotting a iguana on a safari. What does that mean? Pretty easy to spot, right? Because he's the guy he's the leader. He's the safari master. He's got the big safari boss hat. So pretty easy to spot. Why is this easy to spot? Because you're going to have the compound inequality with an unknown function in the middle. So let's just review that again real quickly. You got natural log of x plus x squared less than or equal to j of x less than or equal to e to the x minus 1 for all x except possibly at 1. What is the limit as x goes to 1? Well, I'm just going to go ahead and say, without a highlighter, let's do this. Since this inequality holds true, and the limit as x goes to 1 of the natural log of x plus x squared, what do I get when I use direct substitution there? Does it work? Natural log of 1 is 0, plus 1 squared is 1, and the limit as x goes to 1 of e to the x minus 1, direct substitution gives you e to the 0, which is also 1, so it's going to work. Your lower bound and your upper bound are your two slices of bread, essentially, both pass through the point 1, 1. Therefore, so the limit.
I'm sorry, could you take limit from the left there and limit from the right, or do you want to write it like that?
In this case, it's not from the left and right. It's from above and below. Okay. It's two separate functions. You're looking at the y values now. Okay. These y values contain these y values, which contain these. So you're finding the limit of two separate functions, one from above and below. Thank you. Okay, so the three components of the squeeze theorem: state the inequality. I got lazy here and just referred to it. Find the limits of the two slices of bread, the upper and lower bound. And when they're the same, then step 3 is talk about the limit of the meat that's sandwiched in between the two breads. Should be the same. And if for whatever reason these two bread slices don't have the same limit, then the squeeze theorem can't pinpoint that down to a single number. It could be any number between there. You're leaving some gaps, okay? All right, and so now to review the first real algebraic method that reconciles 0 over 0. Everything before this point right here, the first 5 things we did, were not 0 over 0 or infinity over infinity. Well, I guess the end behavior was infinity over infinity. But here's the first time we've seen 0 over 0, and we've already done this. This was the very first method that we had, the divide out method. Okay, so let's look at this right here. The limit as x goes to 2 of x squared minus 4 over x minus 2. Never not first. What do? Plug in. Now, I guarantee you're going to have a question on the worksheet or a test or a quiz where it looks like it's going to be something that factors, but direct substitution works to remind you to do it every time first. So you plug in and you get a 0 over 0. Now, if you get 0 over 0, it's customary to write it up here kind of above the equal sign. It kind of shows that you plugged in, and later on when we get to L'Hopital's rule, that's going to signify that you're about to use it. So right now, since we have a polynomial over polynomial, and we plugged in a 2 and got 0, we know x minus that number, in this case x minus 2, is a factor of the top and bottom. And that's what's causing the 0 over 0. So all we have to do is factor what's left, and I started this off with the real easy one again. It's just x plus 2 in the top. And then, what happens with your x minus 2s? They divide out, and then, of course, you can use direct substitution right back into what's left. 2 plus 2 is 4. So, again, notice the notation there. Until you actually plug in and evaluate, you need to write the limit each time. Direct substitution, it can go away, and you're done. So that function, whatever it is, has a hole at the point 2, comma 4. So we've already done these before. This was a real easy one to factor. Are they always that easy to factor? They're not hard to factor, right? I hope. All right, try this one. Direct substitution gives us what? 0 over 0. Yay. So we do have a polynomial over polynomial. So indubitably, without a doubt, we know that we're going to be able to factor the bottom into x minus 1 times something. It is just x minus 1. And x minus 1 times something in the top. Go ahead and figure out what the other factor is in the top. The Scorpy. I will. Yes. Davey, you are signing out. So I know that x minus 1 over x minus 1 is what's causing the 0. I just need to figure out what the other factor is. Because look, here's what's going to happen. I'm already anticipating this, right? They divide out, and I just got to plug a 1 into what's left, which I don't have yet. So, any ideas? You did x minus 1, x plus 1? Did you expand it out to see if it worked? Yeah, when you factor out an x minus 1, you're not left with x squared minus 1. When you factor out, you're also dividing out. So if you remember that, what you're really doing is you're really doing x cubed minus 1 divided by x minus 1. And you could do long division, that would work, or you can use synthetic division. Now, synthetic division is going to be nice because we're trying to get rid of a single linear factor of x minus 1. We don't need to factor it completely into the product of 3 linear factors. We just need to factor the x minus 1 out. So synthetic division is an aid to factoring when you know a root. And of course, if you've used direct substitution to start with, you'll know a root. See you, Brooke. So here you go. Synthetic division, you write out the coefficients of the numerator from left to right, 1x cubed, 0x squared, 0x, negative 1. A placeholder for any missing x. And you're going to synthetically divide with the root, which is the number you plugged in. So that's how I do it. I put the 1 right there on the outside. And then this last box right here underneath the negative 1 should be 0, because that's the remainder when you divide by x minus 1, and it's also the function value when you plug in a 1, synthetic substitution. So we bring down the 1. We let gravity do the first step. Then you multiply along the bottom and slide it up, and then add and multiply, and then add and multiply, and you get 0. And remember, these down here are what we're after, because those are now the coefficients of the polynomial that is 1 degree smaller than x cubed. So it's going to be 1x squared plus 1x plus 1. Now, I don't think that factors anymore, but if it did, we still wouldn't need to worry about it, because now the x minus 1's divide out, and we can use direct substitution, and what remains, and we get 1 plus 1 plus 1, which is 3. 3, yeah, you'll get there. Yeah. So this function right here has a hole at the point 1, 3. So it's something we've already done. This is the factor out method, but kind of just showed you a new little trick for factoring when you know one of the roots already, synthetic division. All right, with that in mind, Yugo. Yugo. Used to be a car made in Yugoslavia. I don't think the windows even rolled down. The Yugo. It's a car. Like $500 brand new. Let's see. You doing synthetic division? It's, yeah. Yep. This is about the boogerest you'll see. Remember to write the limit each time until you plug in. Do your synthetic substitution or division off to the side. Did we get opposite signs in a polynomial? Looks like every sign you have opposite to mine. That, you got a 0 though, didn't you? Oh. These are your.
Okay.
Yeah. You changed them as you put them in. Yeah. Okay. Oh no. Okay. This will probably be the last one we get to here today. This one takes a little bit of effort just to plug in to tell that it's 0 over 0 because you got so many signs changing and not changing, but you do get 0 over 0. Being a polynomial over a polynomial, if -1 is the root, then x minus -1 or x plus 1 is the factor. The bottom is a quadratic, so you can kind of infer the other one. But the top one, you're going to really need synthetic division. So coefficients in descending order, synthetically divide with the root of -1. And you will get a 0 here because you've already plugged in. So 1, -2, 1, -4. 1x cubed, -2x squared, plus 1x minus 4. Once you do that, your x plus 1's divide out, and then carefully again plugging in a -1 for any remaining x, it works down to 8/5. So this rational function is going to have a quadratic asymptote. We talked about that the other day. It's x to the 4th over x squared. So it has a quadratic asymptote, but it also has a hole at the point -1, comma, 8/5. What's 8/5 as a decimal? 1.6. Yeah, multiplied by 2 over 2. That could be like a non-calculator multi-choice answer. Not often with decimals. Okay, so I guess tomorrow we'll start with some of the new algebraic methods, like ratcon and lick 'em over lick 'em. That's coming up. Be working on the previous worksheet, and of course, if you get done with that, this one's a fun one. 1.3 is due on Thursday, but this one's coming up right around the bend.